as I'm doing notes here. But again, if you have your notebook and this table out that you picked up on the way in the bond, shape, and angle, you can kind of pick and choose what you actually want to go over here. Now, do you have to know what VSEPR stands for? No. But again, it is talking about how electrons repel one another. Electrons are of similar charge. That idea that electrons will be as far away from each other as possible. And this is what we use to help determine the shapes of the molecules that I'm going to be going over here. Now, an unbonded pair of electrons actually has a greater repulsion than a bonded pair of electrons does. You can see that from the original POGIL packet we did with shape, where it showed something with 4 domains like bent has a smaller bond angle than something with 4 domains like trigonal pyramidal that only has 1 unbonded pair. And the best explanation for that is an unbonded pair is a pair of electrons that is not in between 2 nuclei. So it's not restricted in its kind of how wide out it can expand. It's not stuck in between 2 things. So because it's a little bit more spread out of an electron cloud, there's a greater amount of repulsion there. So the term domain is commonly used of a region of electrons. Again, a domain is either a bonded domain, which could be a single, double, or triple bond. A double bond is still just 1 domain. Or it could be a pair of electrons. And that domain definition you are going to see come up again in identifying hybridization towards the end of the hour today. So we want to be aware of some of that common vocabulary. But again, this VSEPR model of the atom, when we talk about shapes and angles, is dealing with how electrons repel one another. Again, our application of this, taking it a step further, is when we start talking about intermolecular forces between molecules. All right, so I'm going to move on to the next slide. Again, all of these shapes are ones that are on your sheet of paper. So I don't think it's necessary for you to draw or to write all this down unless you are someone who feels that writing it down will help out your memorization. One thing I would note is my 4th bullet point down. The first POGIL that we did on shape, they refer to 3 bonded domains and 1 unbonded domain is just pyramidal. Bless you. Most textbooks call it trigonal pyramidal instead. Trigonal is our kind of front word to mean bonded to 3 things, just like trigonal planar is bonded to 3. If I kind of draw all over the slide, carbon dioxide, again, is a pretty simple example of a linear double bonds on both sides. Boron trifluoride, not only is that a good example of trigonal planar, but it's also a good example of something that has an incomplete octet. So that was one of the ways that the octet rule is disobeyed. Again, remember, for linear, the angle is going to be 180 from here to here. Trigonal planar, as the name suggests, trigonal meaning bonded to 3 things, planar in 1 flat plane, so it's 120 degrees. But once you get past those first 2, now you got to start thinking in 3D, which is a little difficult. It's a lot more difficult to draw, that's for sure, so you just do the best you can. You've seen a lot of these carets pointing out and dashes sometimes going backwards. Tetrahedral, like methane, for example. Again, it's commonly drawn in 90 degrees, but hopefully we realize it's not actually 90-degree angles because that shape is not just in 1 plane. So it has a bond angle of 109.5. Let me erase these so I can keep on just drawing in the same spot here over and over again. Trigonal pyramidal then, things in the nitrogen column with 5 valence electrons usually will bond 3 times and then keep that 1 pair of electrons on the top. So this is an example of that as well. So this would be phosphorus trichloride. And here I did try to not draw flat out 90-degree angles between things. I wanted to kind of demonstrate that that lone pair of electrons is repelling those chlorine bonds a little bit more. So typically a bond angle of around 107, sometimes 107.5. Actually, what you'll find is on the AP, they'll accept a little bit of a range at times for these things. So they are kind of generous. Bent is the last one. In Chem 1, we emphasize this as well, that we should not draw water like this, where it has a pair of electrons above and below. Instead, we should draw it like that. If water were the drawing that I have up on top, if it were linear, it would also be symmetrical. I could cut it in half left and right, it'd be the same. I could cut it in half top bottom, it'd be the same. Water would be a nonpolar molecule if that's what it looked like. Water is not a nonpolar molecule. Water is most certainly a polar molecule. So the bent configuration shows that lack of symmetry, that topic that hopefully you've seen now as we've done that packet to kind of wrap up our bonding part. The very last thing I have on this slide is, again, not all bending is the same because it could just be one pair of electrons on that central atom instead of two. I believe last class there was an example of that with maybe ozone, and it asked you about what the approximate bond angle was, and you kind of had to give a range to make that happen. These last two shapes are the two that disobey the octet rule that I want you to be aware of. These are the two that disobey the octet rule, but are all bonded. So a trigonal bipyramidal, again, I had the models out today, I had the models out last time. You can see there's axial and equatorial positions there. Being aware of those bond angles is something I would want you to know of. So again, those are the last two shapes that I want you to be aware of. That doesn't mean those are the only shapes, because on that table that you picked up on the way in, I tried to not only highlight the entire row across, but then I bolded the shapes that I want you to know. There are other shapes out there. And one of the, again, adjustments that the College Board made a few years ago when they rewrote the AP Chemistry requirements was they decided that students did not have to know every single shape of molecule that there is, which is probably to your benefit. At the same time, I'm just going to show you on the next slide a few of these other shapes that are not required, just so you are aware that there are other things out there. I kind of drew in the elements as we went along as well. I believe the SF4 was one of the very last questions in the POGO packet you just did. So it's bonded to 4 things, but there's a pair of electrons. Notice how in all of these on this page, fluorine is the terminal atom, the atom that's at the end. This is pretty common because in order to disobey the octet rule, you are going against one of the kind of fundamental rules of stability. But fluorine is the highest electronegative element on the periodic table. It's kind of a bully. It will try to take what it can. On this bottom example here, I have xenon, a noble gas. We try to drill in Chem 1 students the idea that noble gases are not going to react at all. They are stable. However, xenon is so big, its outermost electrons are very far away from its nucleus. Fluorine can attract those to create bonds because fluorine needs to bond. It's the highest electronegative element there is. It has a very good tendency to attract others' electrons. You take these things in a gaseous state, you put some pressure on them, so you squeeze them close together. Fluorine will try to pull on these other things' electrons. But none of these shapes on this page are ones that you are required to know. I simply bring them up because they are ones that exist. Now, again, practice tests for AP kind of vary because some are predating the changeover where they actually, I've seen a question address the SF4 molecule before. But it's not as likely to happen that way. By the way, my last 2 slides on this is just the table that you went over. Again, to me, it's important to recognize what are the angles. Notice I left the bent angle blank because there's variation depending upon how many unbonded pairs of electrons there are. By the way, there is a linear form that has 3 unbonded pairs of electrons, a xenon difluoride. You might have saw that in the POGO packet. And then my last slide, again, was just trying to fill in that table kind of a little bit, but you already have that table with you, so you should be okay there. We go over shape of molecules because it will slowly relate to how two things interact, be it dissolving, melting point, boiling point, so the things that determine what we call intermolecular forces between molecules. What we need to transition to next, which is actually ties in well with this, is bond hybridization, another theory of bonding besides that VSEPR theory, which is the basis of all of this. Again, there is no one theory that explains all of bonding. There's actually one theory of bonding that we don't cover anymore called bond order. I've never seen any major emphasis at all in the College Board on identifying bond order, so it's something that we don't do, that your textbooks would go over if you wanted to look at it. But what you're going to do with the rest of class is first do the computer activity for hybridization. It's going to remind you of electron configuration and then tie that into hybridization. And then from there, you picked up another sheet that's similar to this table of bond stuff, but it has more blanks and more things on it to add to it that ties in hybridization and dipole moments and things like that as well. I think it's a good kind of wrap-up sheet that we have to wrap up our day then. Okay, so computer activity,